Yeah, can you record it? Yeah.
Yeah, it's a recording.
So get it. You press this, or you press.
I did it.
On the screen, I think. Or it's on this screen, you can do it too.
Yeah. Great. Okay. Let's start today. It's a great pleasure to have an in-person seminar by Joao Barata from Brookhaven, and he got his PhD from Santiago, and like 2 years ago.
No,
Last year, yeah. So and then it's a great pleasure to have him to come for a personal visit, and then we have a seminar today for joint theory seminar and heat, and he will talk about jet evolution in anisotropic plasma. Please go ahead. Yeah.
So let me first thank for the opportunity to come here and to give the seminar. So as Xineng said, I will talk about, my talk will be about jet quenching theory, and in particular I will explain.
If you want, there's a. But the remote people can't see it. So
I will use my pad.
Yeah,
I think it's fine.
All right. Sorry to interrupt.
No problem. In particular, I'll talk about jet evolution in anisotropic plasmas in terms of, the theory calculation behind this. And this is based on, this paper that I wrote at the end of my PhD, and then with people from Santiago, and then some more recent paper with Xinyan and Andrei Salofiev, and also some ongoing work with the group in Santiago. So before I go into the detail, let me just give you a very brief overview. So of course, the goal of jet quenching is to study the properties of the quark-gluon plasma that is produced in heavy ion collisions. So in this plot here, I show a very nice picture of what happens in heavy ion collisions at high energy. So essentially, before the collision, the nuclei are very contracted into these pancake shapes. And after the collision, there is a production of the quark-gluon plasma, which in this plot is this red dot. So it's a very hot state, so the temperature is very high, and essentially the quark and the gluons are out of, they don't have to be confined anymore inside the atoms. And the point is to study the properties of this state, and of course, because this is a collision, at the end, all this matter expands, and what you see at the end is this collection of atoms, from which you try to infer what happened at earlier times. Of course, motivations to study this type of events is very broad, but very briefly, to motivate these studies, essentially the main motivation, I would say, is to understand the properties of the quark-gluon plasma, because it's an exotic state of matter. But besides that, the study of heavy ion collisions also provides a way to study in detail the phase structure of QCD, in particular the transition between the quark-gluon plasma to the anionic phase. And at very high energies or small chemical potential, you can also, if you evolve along this line, this is similar to the evolution of the universe from early times to the present epoch. Okay. So as I said, the goal of heavy ions of jet quenching is not to study just the modifications of jet, but to try to infer from the modifications that we see on the jet spectra what happened in the evolution. So in this plot, what I'm showing is the evolution of a jet, which I will show afterwards, as this collision happens, and essentially the modifications to the jet can happen in 3 different stages. So at early times, essentially, what one has is the dominance of this plasma phase, which is dominated by these very strong fields, which are governed by the classical Young's equations. But essentially, for jet quenching, most of these modifications, although this is still studied, are ignored because this is a very short time-lived phase, and most of the modifications come from the proper quark-gluon plasma phase, which is long-lived, and this is where all the calculations that I will show are performed. Of course, afterwards there is also an anionic phase, and finally the freeze out of all of the interactions. But it is the effects on the jets coming from this stage are expected to be much less significant than compared to the intermediate stage. Okay, so and the main modifications to the jet are illustrated in this picture. So on the left-hand side, what I'm showing is a jet event detected by CMS, and what you see is the jet going back to back essentially, and you see that all the particles that come from this these are the events are collimated into this region, and this, once you identify all of these particles with some algorithm, this is what we call a jet. When you go to lead-lead collisions, or where there is a production of the QGP, first of all, you see that the background is much more complicated. But even though this is complicated, you can still reconstruct the jet. But what happens essentially are two effects. So the first one that you can see here is that we have a jet which is essentially not very modified by the medium, meaning that this is essentially where the jet that was triggered. And you see that the amount of energy deposited or lost by the jet is not that much. But when you look to the waste side, you see that there is a large energy imbalance. And this is because most of the energy of this jet was deposited into the matter. The other effect is, on top of this energy loss, also the broadening of the jet structure, meaning that the jet cone is no longer so collimated, and that's what is exemplified. So these are essentially two main effects that happen to jets due to evolution in the medium. Now, when you go and try to compute this type of modifications, it's a very complicated problem. And here I try to illustrate essentially what is the picture that one has when these calculations are done. So essentially, the idea is that if you look inside of this object, what you would see is that essentially there is an initial arc process which happens at the same time as the collision of the two nuclei. And what happens is that there is still this blue cascade here, which is kind of the virtuality cascade. But at the same time, these particles inside these cascades can still interact with the particles in the medium, which are denoted by these gluon exchanges with these blobs. And what these interactions do is, first of all, since there is a momentum exchange, they deflect the trajectories of these particles. And because you are deflecting the trajectory of a charged particle, you can also create or induce the production of radiation like this, which are represented here by these red gluons. And the goal of essentially all of these calculations is to try to compute this type of diagrams. Of course, this is very complicated, and usually the main focus in theory is to compute the simplest cases, which is either no gluon emissions or only the first to compute a single emission. So the way this is done in general, so there are many formalisms to tackle these problems. So they differ from each other quite significantly in the sense of the way the calculation is performed, but they kind of agree in the sense that they have the same picture for the interactions. So today I will talk about three of them, just to illustrate essentially what is the usefulness of using different formalisms to try to get different answers. But most of them are based on perturbative QCD, so they agree up to some approximation. And of course, there are some more exotic approaches, but this I will not talk about today. One important point is that although there are all of these different formalisms, they have kind of a common set of approximations. Of course, in the details they differ a bit, but essentially the idea is that one assumes from the start that the jet is much more energetic than the typical scale of the particles in the plasma, which would be the temperature of the quark-gluon plasma. And this essentially allows one to do an equatorial expansion in powers of 1 over the jet energy. And typically, we just keep the leading order terms in this expansion. The other big approximation is that the way we model the matter, so the quark-gluon plasma, is to assume that it can be described by some classical field or stochastic field. And then on top of that, in many calculations, there is an assumption that the medium is homogeneous, infinitely long static, which is kind of the perfect picture. So essentially, the point is that you go from a real event where the medium looks like an almond shape, so it's expanding and it's not expanding in the same way in all directions, and you shoot a jet through it, and you go to this picture where essentially the medium is just a brick that is fixed and not evolving, and you just evolve a particle through the medium. So of course, this is probably not the best model for this event, but the good thing of doing this is that it gives insight into the important scales in this problem, and it gives you some information, analytical insight into all of this business. But of course, the problem is that once you take all of these approximations, many of the effects of the evolution imprinted into the jets are lost. And this is bad because the goal of jet quenching, of course, is to infer the properties of the matter by looking at the jet spectrum. So that's why this is not good, and one would like to essentially remove some of these approximations. So that's a motivation to go beyond all of this work that was done in the last 2 decades. And there are many ways to go about it. So one way is kind of standard way coming from QCD is to go looking into QCD type corrections to this type of processes. So these are like relative corrections to all of these processes, and of course these are important if you have like some large logs. But besides that, you can also look, for example, at subaquantal correction, which is keeping track of terms which are suppressed in this energy expansion that I mentioned, and also another important point, which is what I'm going to talk about afterwards, is also to improve the way you model the matter where the jet is evolving. And the reason why these things are important, so compared to the QQCD ones, which are usually enhanced by some large logs, is that these ones are either, so this type of corrections will be power-like in the sense that they are not enhanced by logs, but they can be important because they can be enhanced by some medium parameter, for example, the medium length, or they can be a leading order effect, meaning that if you don't include this effect, there is nothing in the calculation that shows this property of the underlying matter. And this becomes even more important because in recent years, of course, the goal is to go deeper and deeper into the details of the jet structure using substructure techniques or going to jet tomography. And to do this, you need to model better the modifications of the jet imprinted by the medium. Okay, so what I will discuss today is to go in one of these directions and to essentially study how jets evolve when the medium is no longer just a brick, but it also has some structure. So essentially the point is that having this picture for the medium is not a good picture when you want to model the medium as a fireball, and this is what you want to capture because this type of modeling doesn't take into account that, for example, this matter has some gradients inside of it. Of course, this is also important because as we know that the evolution of the jet through the medium also modifies the medium, and this is what people refer to as medium response to the jet. But of course, this effect is not decoupled from the fact that the medium also modifies the jet, and you cannot decouple both of them. So of course, if you want to improve your understanding of medium response to jet evolution, you also need to improve your ability to describe the jet reaction to the medium modification.
So it's a anisotropic, but still infinitely long-lived medium.
So I will show it later, but in this case, it's finite medium, but it's static. The point is that the static approximation can be lifted, but it's much easier compared to the transverse direction. So but I will show it later. Finally, I mean the other motivation is that actually many years ago, people tried to compute this type of effects for not for gradients but for flowing matter, which is similar. But what happened is that what was done was not like a real calculation from first principles. What was done was more like they modified the effective potential through which the jet interacts with the matter, such that there is some sort of bias towards some flowing direction of the medium. This is what this shift here does. And although, I mean, phonologically, you will get the right qualitative picture when you do the calculation, this is not what should be done. So the calculation that I will show is essentially how to implement this effect starting from the first principles calculation within the framework of jet quenching. Okay, so essentially what I will talk about today are these two topics. So the first part, I will describe how to compute the leading order observables, which is just the broadening of the jet. So this is just how does the distribution in momentum of a single particle get modified due to multiple interactions with the particles in the medium. And then I will describe the first order correction, which is when you have the emission of a gluon on top of this. And on the second part, I will describe how this discussion can be formulated into some sort of effective kinetic theory approach. Okay, so as I said, first I will describe broadening. So essentially the problem is summarizing this picture. So what I will do is that I will shoot a particle which has some initial distribution, which is modeled by some current J through the medium, and I will assume that the medium has some anisotropic direction, which I denote by this grad of T, which you can think as being, for example, the direction over which the density is increasing in the transverse direction with respect to the jet, to the direction through which the jet is propagated. So at the end, what I want to determine is what is the distribution of this particle distribution at late times in the transverse plane with respect to the longitudinal direction. Okay, before I do that, let me just briefly tell you how we usually model the matter in all of these calculations. So here I show you kind of the proper diagram that you should compute. So essentially, if you have a particle in the jet, which is what these lines mean, it can exchange a single gluon with a medium, which then also has some quasi-particle here. But what we do in jet quenching effectively is that we cut this diagram and just replace all of this bottom part by some classical field A. And then we essentially say that this classical field A can be reconstructed as a sum over of different sum of the contributions from different particles, where each particle essentially gives you some effective potential V. And on top of that, we make this approximation that there is no energy exchange through this interaction. And this is, so the way you get this is because this is kind of the leading order. So when you do diagonal expansion on the momentum conservation condition, which is either inside this condition, inside this delta function, you get that there is no energy exchange. And to model these potentials that are produced by each particle in the medium, we use some model, and all in this calculation we use the GW model, which takes this form. Which is, as you can see, it's just the propagator of this gluon screened by some mass, which is a Debye mass. And the second part is to define the statistics of this field. And what we use in jet quenching is that we use this Gaussian approximation. So the only relevant correlator in the field is this 2-point correlator. And in practice, what it says is that, for example, if you have a diagram like this, where the particle, the jet interacts with the medium on the left of the, so on the amplitude and the conjugate amplitude, when you average this over all possible configurations of the medium, essentially just identifies this particle with this particle, and it's like the interaction is the same on both sides of the cut. Okay.
Hi, Joao.
So,
I have a quick question.
Yes.
So this conservation of energy, is that because you're considering the medium as a static?
I mean, this condition here, the way to derive it, I mean, the way I see it is that if you write here the condition that this particle has to be on shell, and then you just expand it in powers of 1 over the jet, 1 over the energy, the leading term would be this one. So there are corrections to this one, which are, I mean, the corrections to this one are like collision, energy loss effects due to the elastic collision between these two particles, which we don't take into account in this calculation.
Okay. Thank you.
So wait, that just makes Q0 to 0?
Yeah, so essentially in this exchange, you can only exchange a transverse momentum. So there is no energy transfer. So Q0 and Q0 are not changing in the interaction. Which, of course, I mean, this simplifies calculations a lot, otherwise it's much more complicated. Okay, and now, I mean, since having this, it's kind of easy to compute this using kind of the standard approach in any calculation, in any calculation. So what is done, essentially, is that you just compute all the diagrams with all possible insertions. And one way to do it, I mean, the organized way to do it is just to do it in order by order in the number of interactions with the medium, such that if you want to write the squared amplitude, you can just decompose it order by order in the number of interactions. So here I wrote down the diagrams for the single interaction, which is either on the amplitude and conjugate amplitude, or a double interaction in one side of the cut. And then once you compute this diagram, which is trivial because they are 3 levels, you just have to average all of these quantities over the all possible configurations of the background field. And the point is that doing this is simple in the case of an homogeneous medium, because the way it's done is that you assume that you can replace this averaging as some integral over some density of scattering centers in the medium. And in the case where the density rho doesn't depend on the transverse position, which is just saying the medium is homogeneous, it turns out that this procedure is very simple. In particular, what happens is that the squared average amplitude with n insertions is just a product of the so it's just a product of n This is much nicer. So essentially, the idea is that in this approximation, each insertion becomes decoupled from all the others. So when you have n insertions, you just have to put n of these v's, which is some effective potential, which takes into account real and virtual gluon exchanges. But the point is that because all of these exchanges become decoupled from each other, essentially at the end of the day, they just exponentiate into this form. And that's the trivial result that we use. Now,
Are you supposed to point to that screen or to your laptop?
I mean, it's pointing there, I think. How do you put it? How do you fix it?
Oh, you have to press this. Oops. Back. You press this button and to fix it, and then oops. Oh, press this button, fix it. Then it doesn't move anymore.
Oh,
Yeah.
okay, sorry. So now, if you want to do this calculation for a case where the medium, for example, the density depends on the Druse's position, it's more complicated. But what we use here is the fact that essentially in the quark-gluon plasma phase, so the quark-gluon plasma behaves as like a perfect liquid, so you can expand it. I mean, it can be modeled by hydrodynamics, and so since hydrodynamics is expansion in gradients, we can also do an expansion in gradients in the thermodynamical parameter, which in this case is just the density and the Debye mass. Okay, and once you do this, it's a bit more complicated because essentially now every time you have a scattering, it's not really independent from the previous ones, but it's not so bad because what happens is that you get the so what happens is that instead of just getting n independent scatterings with insertion of these potentials, you get this thing in between, which is suppressed by 1 power of energy, but you can still write it down. And then this is the nth order contribution, and then you can just do some brute force calculation and resum all of this series, and it's taking order in gradients is still feasible. So this is this result is correct, but it's kind of very brute force, and it's hard to generalize if you want to compute more complicated observables. So one nice thing about this formalism that I showed is that you can in principle compute everything. Is just very hard work and hard to see how things generalize to higher orders or for more complicated observables.
Joe, just to be sure, the result that you just showed on the previous slide, this only takes in consideration the first gradient expansion, right? Is that correct?
Yeah. Okay. Yeah. So this formula here is only valid up to a leading order in either grad mu squared or grad 4.
Okay.
So there are corrections which are not accounted for at this level. I will comment on the properties of this function later.
Thank you.
So, okay, so now I want to show how you can, essentially by using another formalism, you can actually compute high order corrections in gradients, essentially by doing the calculation in a smarter way. So this
you mean high order in gradients?
Yeah, in gradients, yeah. So the formalism here is this PDMPS formalism, which are just names of people, but the important point is that instead of just computing diagrams and resumming them brute force, what is done is essentially first when one resums at the level of the propagators all possible insertions of the field. So essentially there is some effective propagator G, which takes into account the evolution in the vacuum or the evolution with a single scattering and so on. And it turns out that for the approximations that are usually employed in jet quenching, it turns out that you can resum this G to have in terms of this path, path integral. And the only point is that it has this kinetic term which takes into account the possibility of the particle to move in between two scatterings. And then it has this potential which just describes the interaction of the particle with the particle in the medium. Okay, and then what is nice is that once you know the form of this propagator, if you want to compute exactly the same diagram as I showed before, you just write down the usual Feynman rules, which is just this diagram, and then the squared amplitude already resummed just takes this form, and essentially the only difficulty now is to compute this two-point correlator exactly. which of course is difficult because this is the correlator of two path integrals, so it's, essentially has not done anything so far. So there are two options. One option, of course, is to break down the path integral and just compute it order by averaging each term, but this is, mathematically the same as what I showed before. And what people usually do is instead to first perform the averaging and then to solve the path integral. And this is only possible because we use a particular form from the averaging, which follows from this Gaussian approximation that I mentioned before, which just tells you that this, so the statistics of this correlate this potential here, take this very simple form. And in particular, it means that the correlator for this path order exponential here, with its conjugate, can exponentiate this effective potential that I showed before. And this is the trivial generalization of the distribution that I showed in the beginning by just computing all the diagrams with force. Now, when you go to an anisotropic medium, is a bit more complicated, but you can still show that at leading ordering gradients, the averaging is of this form. So it's essentially the same result, but now there is also a term which depends on this, on the gradients, but also on this coordinate, which you can think of as the center of mass of the system, where the system now is kind of the dipole formed by the quark in amplitude and conjugate amplitude. Well, before it only depended on the separation of these two of this dipole. In particular, what is non-trivial to show, as I will discuss afterwards, is that this property also follows at the level of the path order exponentials, meaning that when we exponentiate the deal, which we just got this effective potential, it also works out at leading ordering gradients to this form, which of course should expand now to be the usual result plus some linear function in the gradients. Okay, and then once you have this, using techniques that I will not discuss now, you can solve this complicated path integral, and you will find exactly the same solution as the case for the brute force calculation. Okay. So now let me just essentially explain to you what are the properties of this distribution that we found. So essentially, you can write the particle distribution as a function of x, which is the x in transverse place, takes this form. So P of x can be understood as the Fourier transform of the momentum distribution, which just tells you that when you Fourier transform this object, it tells you essentially what is the probability of the particle acquiring momentum P inside the medium. And in the usual case, this S operator in the middle is just the unity operator where you don't have the gradient. So this is like a classical interpretation. In our case, it's a bit more complicated because essentially the decoupling between this distribution and the initial distribution from which the particle is produced is not, it doesn't factorize as a product, and then this breaks this interpretation that we had before. Still, you still have that this thing conserves it's still unitary, meaning that the evolution in a medium cannot increase or decrease the number of particles, which is what this condition means. Now, if you compute this numerically, which is what I'm showing here, so here I use this GW model and I did the calculation of this P distribution exactly in the computer, ignoring this initial state effect that comes from this S operator. So this P you can interpret as the momentum acquired, so the probability of acquiring momentum P due to evolution in the medium, assuming that initially the particle has no transverse momentum. And this can be written essentially just as a function of this angle theta and this quantity Ct, which measures how large the gradient effects can be. So theta measures essentially so it's the angle with respect to this direction. So if theta equals to 0, is aligned along the direction where the gradients are largest, and if it is equal to pi, it's anti-aligned against this direction. So what I show you in this plot is this distribution P weighted by the Jacobian as a function of the PT of the particle. And what you see is that when the particle is aligned along the gradients, essentially you shift the distribution towards higher momentum, which just means that the particle will tend to bend along the direction where the gradients increase. And of course, if you go against the direction of the gradients, you deplete the high momentum region and you populate lower momentum nodes. And all of these effects are controlled by this chi, which is the medium opacity. So essentially it tells you how many scatterings on average the particle will suffer in the medium. So in this case, it's 15. And this is related to this parameter Q hat, which is a jet quenching parameter, which understand the approximations, you can understand it as the effective diffusion coefficient in the mean. So essentially, at the end of the day, the phonological effect of gradients is just they tend to bend the particle along the direction where the gradients increase. So now,
Joao,
yes.
sorry, can I ask another question? So in the plot that you showed, why is there this interesting deep structure? So there is a curve that goes up, that goes down, and goes up again. How can we understand that feature?
Yeah, so I mean, so in this picture, I'm not using like, so I'm using very large values so that you see this feature like it becomes very prominent, this shift. But the point is that, although it's hard to see from this formula, what happens is that what these gradients will do is that they shift so they will shift the distribution to have larger values at higher KT, but the shift comes from the peak of the distribution. So essentially, the peak is determined by the saturation scale. I don't think I have the formula. Yeah, sorry, I don't have the formula here, but you can see, I mean, from the analytical calculation, that essentially the depletion comes from removing probability from the scale where PT is equal to QS and putting it at higher modes. That's why you have the dip here, and essentially you can see that when PT is of order of the Debye mass, which is this region here, you don't touch it, and that's what should happen, because otherwise the calculation would be sensitive to non-perturbative physics, which would not be good.
So this curve corresponds to the particle moving in the direction of the gradient. Is that correct? Am I reading the plot
Yeah.
correctly?
So the dashed ones are the particle moving along the direction over which the gradient is increasing, and the solid ones are when we force the particle to move against the increasing gradients. So they are moving against the direction over which the.
But the difference between the two dashed lines is this CT. What is the
Oh,
CT?
yeah. Yeah, so CT is what I was trying to explain before. So CT is just a parameter, is just a dimensionless parameter that
it's the center gradients, right?
Yeah, so it's just it doesn't, I mean, so essentially in all this calculation, since we don't have a model for the matter, I cannot tell you what are the gradients. I don't have a formula for the gradients, right? So I just construct these dimensional constants that tells you how large the gradients are. So the difference between the red and the green lines is just that the red lines have smaller gradients, and the green lines have very large gradients.
What is your theta? What is your theta again? The theta angle is respect to what?
So the theta angle is the angle in transverse transverse space. With respect to
zero means it's just along the.
In that picture.
Yeah, I mean it's in the picture.
Yeah.
So when theta, so I mean maybe the picture is not the best, but this blue line is in the z direction, so longitudinal direction, and then on this transverse line.
Okay. It's respect to the original part direction, essentially.
Exactly. Yes.
So when you look at the one theta equals pi, you are looking at a wave. I mean, is that possible? I mean, you're saying that the jet essentially turn around.
No. I mean, so you can look at any angle, but essentially it's like a modulation by cosine, so you don't care. So the point is that you can look at any angle in the transverse.
I'm sorry. It's back.
That's the beam.
It is
the beam angle. And that is
you should use phi instead of theta. This is so as azimuth angle. It's this jet direction. You're looking at the gradients. You're looking at this angle.
Yeah,
right?
yeah.
Not this angle.
No.
Okay,
because I mean that would not be.
Yeah, that looks like I understand.
Yeah, this is supposed to be treated.
It's respect to the gradients.
Yes.
Okay, not the beam direction.
Yeah, so I mean, although I didn't show, I mean, you can. If you make this plot as a function of theta, what you'll see is like a cosine modulation.
Sure.
Because that's why I only picked two angles, because the other ones are just like multiplying by a factor. Okay, so now.
Joao, sorry, yes. I think Peter has a question. On the Peter, can you please go ahead? Unmute yourself.
Same question, but sorry, I'm remote, so it's hard to understand everything in the room. So this is the deflection relative to the initial parton direction, correct?
No, so it's like you should. Okay, so this blue line here is the longitudinal direction. So it's like it's the z direction over which the jet is propagating.
But that's the direction of propagation in the absence of a medium. Maybe I misunderstood.
Yes. Yeah, but I mean in this order, because I mean it doesn't, this direction doesn't change due to the medium, because the medium only deflects the particle in the transverse plane, but it's always propagating along the same z direction.
I understand that, but if I think experimentally what this would mean, you need a coincidence channel where you trigger on a photon and you look backwards for a jet. That's what you have in mind. So the photon defines an axis.
Exactly. So I mean, experimentally, for example, if you have gamma jet, it would be like gamma would be. You can see my cursor, right? Gamma would be here, and then this would be the direction defined by the photon.
Yeah. So I mean, maybe you get to it, but the vacuum effect, Sudakov radiation, which will broaden that distribution naturally anyway, and these medium effects are on top of it. So do you consider those together, or are you just considering medium effects?
No, I mean that's virtual effect. So I'm only talking about medium induced effects, not the virtuality cascade. Of course, the Sudakov will also change this, but this is not taken into account here.
Right.
Okay, thank you.
Okay, so then, so now if you want to compute the Gluon distribution, which is what I in the beginning said, it's what it's usually computed in this field. So essentially, the problem is a bit more complicated, but in the simplest setting, what one does is you again start with some distribution for the quark, but you assume that the quark essentially is moving. I mean, it's so energetic that it doesn't see the medium, so it doesn't see any modifications. But what happens is that you allow the quark to emit a very soft gluon, and what you want to compute now is the distribution of this gluon in the transverse plane with respect to the longitudinal direction over which the quark or the jet is propagating. So the calculation in the reasonable brute force way is very, very complicated, but that's why I try to show that you can do the calculation using this recent formalism, because in this formalism it's kind of trivial to do it. So essentially what one has to do is again just write the relevant Feynman diagram, which is this one. And then this Feynman diagram essentially comprises three regions. So essentially there is first the initial currents which describe the initial distribution of the quark. Then there is an intermediate stage where essentially the gluon is being produced either in amplitude or conjugate amplitude. And this region determines essentially how the spectrum of the gluon spectrum behaves. And then at late times, there is just the evolution of the gluon, which is just dominated by the kicks of the gluon in the medium. So essentially, when you work this out, what you find is that the green region, which describes the emission of the gluon, is given by this object kappa, while the late time evolution is given by this object, which is, I call it S2, but S2 is just a particular form of this P distribution that I showed before. And kappa, you can show that is just another different correlator from the one that I showed before. So the previous one was G dagger, and this one is G convoluted with a Wilson line, or so Wilson line, which is path forward exponential. Okay, and then you can use similar techniques to what I showed before and just work out what is this object leading ordering gradients, which is just a very simple exercise in perturbation here. Okay, and then when you compute the spectrum here, so the gluon spectrum here as a function of the omega, which is the gluon frequency, and k, which is the gluon transverse momentum, as a function of the gluon transverse momentum, what you find again is a similar behavior to what I showed for the Brownian distribution. So when the gluon is being emitted along the direction where the gradients increase, it will bend. So the gradients will bend the gluon along this direction, and if you emit the gluon on the other direction, it will not bend so much. Of course, here it's more complicated to see because the other plot was simpler because there is a unitary condition which tells you that if you remove some probability from a part of the plot, it will show up later. But here it's more complicated because it's differential in energy and heat. And finally, I mean, although you can compute this, what is also important is to note that this distribution obeys a classical picture which is used. So, for example, if you want to do Monte Carlo implementation, which just tells you that the full Gluon distribution the gluon spectrum can be written as a convolution of this Brownian distribution for the gluon being emitted at some time z, convoluted with the rate of emitting a gluon with frequency omega at some finite time. And this, of course, is very useful because this tells you that there's a separation between the KT and the energy distribution.
Your zero direction is in the direction of the gradient increasing or decreasing. I mean,
so
the
in this case, if when the medium will tend to bend the gluon towards the direction where the gradients increase.
So that's the zero direction. Right?
That's the zero direction. Yeah. So this this CT and this theta are the same.
Yeah. Okay. That makes sense because apparently your pi is essentially away from the gradients, so you have more radiation spectrum than against the radiance. I'm just comparing to the two figures.
Yeah.
One is theta equals 0, which is essentially against gradients, and the pi is essentially away from the gradients, I think.
Yeah, so I mean, the way to see it is that when you are along the gradients, you see that this peak gets reduced, and I mean, it will appear here that this is slightly increased.
No, you compare to left and right. I mean, the two figures, right? Yeah.
Yeah, so when you are moving along pi, you get the peak going on the other direction compared to the vacuum, which is a solid. I mean, the reason why you cannot see it so clearly is that because this is not normalized to unity, it's normalized to standard. It's more complicated. Okay, so far what I showed is how to compute this, explicitly how to compute these distributions, essentially in perturbation theory to leading order invariants. The point is that, to go beyond leading order is quite hard to win these approaches. I mean, unless you just sit down and do, perturbation theory to second order. But the number of terms that you have to take into account increase very rapidly. So to do this, what we use is instead to look into the kind of the effective kinetic formulation of all of this problem. So essentially, the idea is the following. So in all of this discussion that I had of how to describe the evolution of the jet in the medium can also be formulated in terms of the evolution according to some transport model. So usually what people use is this reduced form of the Boltzmann equation, which essentially, so F describes the particle distribution for the particles in the jet in terms of their PT and X, so the position in transverse place as a function of time. And here on the left, you can either include the 2-to-2 processes. So these are the processes that describe the interaction of the particle in the jet with the particle in the medium. And also you can include the kernel, which describes the emission, for example, of the gluon, which is a 1-to-2 process. This, which I will not discuss here. But the way to obtain this type of the explicit form for this equation is either to do a proper kinetic theory calculation, which is not what I do, or instead what is usually done is essentially to construct, for example, for the P observable, for the P distribution, is just to try to reconstruct what is the evolution equation that it obeys. So for the P distribution that I showed before, you can show that it satisfies this equation, which in some particular approximation where essentially one assumes that the momentum exchange between the particles in the jet and the particles in the medium is always very soft. It tells you that this object satisfies a diffusion equation, which is why I said that this object, the jet quenching parameter, it can be interpreted as the diffusion coefficient. Now the challenge now is that we want to compute this not for an homogeneous medium, which is where this P distribution is valid, but for an anisotropic medium. So one way to do it is to construct this Wigner function for the quark. So this Wigner function essentially describes the distribution in terms of the momentum of the quark, transverse momentum, and also in terms of the transverse position in the medium. Okay? Which, of course, if the medium is homogeneous, it becomes trivial in this variable. And what you can do is, so this object takes this form, which just depends on this correlator, which is essentially what I computed before, although it has, so this one is a bit more general because it has more general coordinates, but it's essentially the same exercise. And since we know this object to first order invariants, we can just directly compute the evolution equation. And what you can show is that this object satisfies the Boltzmann equation with this particular form for the 2-to-2 kernel. And the point here is that this 2-to-2 kernel is just the usual diffusion coefficient summed with this the gradient of the diffusion coefficient in turn with the position in the transverse. And this is important because it's just telling you that essentially if you want to simulate, so essentially if you want to couple your calculation which was done in an homogeneous medium to a proper description of the geometry of the quark-gluon plasma, you can just do this by saying that essentially replacing the homogeneous diffusion coefficient by diffusion coefficient that depends on the transverse position. And this is what people usually do when they do kind of more proper phenology in jet quenching. But although they do this is not like proper because it's not proper in the sense that these things don't commute. So doing the calculation on a homogeneous medium is not the same as using the non-homogeneous coefficient in an homogeneous calculation. Of course, what you can ask afterwards is when does this stop being valid, meaning replacing this by an anisotropic coefficient. And the clue to see where this stops to being valid is to look again at this correlator that I showed before. So before I claim that this object can be exponentiated in this form. And if you look at what people do usually is to write this object in this way. So essentially, this V gets replaced by this R squared, and then all of the dependence in the anisotropy gets replaced into just putting it inside the diffusion coefficient. And that's why this approximation that people do here works, because essentially when you do this approximation, you lose track of all the corrections. But in fact, if you do the calculation from the beginning and you compute this object to second order ingredients, you will find out that this doesn't work and doesn't exponentiate anymore. Okay, but in fact, since in the kinetic approach we never compute explicitly the Wigner function but only the evolution equation, we can go further and compute the general evolution equation which resums all orders in grade. And to do this is very simple, but essentially what one does is just to look at these 2 point correlator that I showed before, between 0 and L plus some small epsilon can always be written as the evolution from 0 to L plus from L to L plus epsilon. So essentially this small correlator here tells you what is the evolution kernel in an infinitesimal step. And I mean, diagrammatically what you are saying is that the Wigner function, which is this block here, which has 2 indices, which are k and k bar, can be written as the initial Wigner function, which is this block here, plus some evolution. And the evolution is either vacuum evolution, so nothing happens, either there is a gluon exchange with the medium, or there is some virtual correction on top. And what you can, oh, I think I lost connection.
No, you're good. We can hear you.
Oh, no, I think you lost.
Yeah, we cannot see your slides right now.
You lost connection?
I don't know.
Yeah, you're still there. Oops. You can share a screen.
Yeah, I'm sharing. Okay, sorry. So then essentially, I mean, once you work it out, you can show that the full evolution equation, which we sum all orders in gradients for the Wigner function, takes this form, where essentially just determined by some particular kernel, which is R2 interval. So finally, the way to understand what happens now is to take this equation and expand it order by order in gradients to see what happens when you go beyond AD1. So of course, at 0 order, as I showed you, just get the diffusion equation. At first order in gradients, what you get is a diffusion equation with a diffusion coefficient, which is now dependent on the position of the quark in the matter. But when you go to second order in gradients, is more complicated. So you still get this term, which is just obtained by replacing the usual diffusion coefficient with the one which is dependent on the position, but the second order ingredients. But on top of that are a new term which you can interpret as quantum corrections. And this is the full equation to second order ingredients. And these terms in a box are these quantum corrections. The reason why they are quantum corrections is because if you try to derive the equation to orders ingredients in kind of some naive kinetic approach, you realize very soon that essentially all the terms on the right-hand side must be zero if you assume that interactions are local in this impact parameter y. So essentially, if the interactions are not local, that's where you can get this type of terms. And of course, this is not included if you start from the Boltzmann equation, because in the Boltzmann equation, all interactions should be local in this coordinate. Okay. So finally, let me just show you very briefly one quantity that you can straightforwardly compute from this equation. So here again, I'm computing kind of the total diffusion coefficient or the jet quenching parameter Q from this Wigner function. And what you find is that the full coefficient here can be written as the homogeneous coefficient times corrections which scale with the Laplacian of the diffusion coefficient. And there are two types of corrections. So one of them is a sub-subeconal correction, which it just appears because essentially the expansion in gradients doesn't commute with the expansion so the diagonal expansion, and because it doesn't commute to get corrections, which is when there is this interplay between these two expansions. These corrections are very small because E is typically very large, and this scale here is for sure it's much smaller than this one. But on top of that, what you can get is a correction which is energy independent, so it's leading order in diagonal expansion. And you can compute it directly if you define a particular model for the medium, which is not. On the right-hand side, what I'm showing is a different computation, so it's not this computation, but what we did here was so essentially we prepared an initial state, which is a quark, and then we time evolved it in real time, and then we measured the momentum distribution at the end. And then we computed Q from this final distribution. And what we did in particular in this calculation is that we use the medium where there is a background field, which is the homogeneous one, and it's then modeled by some distribution which mimics the fact that there are some gradients in the medium. And what you see here, in fact, is related to this formula. So you see on the open symbols, you see the case where the quark has infinite energy, and the closed symbols are the quark has finite energy. And then the red case is when this is in the vacuum, where it's in an homogeneous matter. And this case is when there is some finite gradient in present. And you see indeed that although the difference between the finite and infinite energy cases are small, which is related to this coefficient here, which, as I said, is very small, there is still a constant correction which scales with the medium parameter, which is what we showed analytically. Of course, this is you cannot compare them together because to model this calculation in the way that we did it, it's difficult. But at least here it gives you a feel that this type of correction here can be somewhat, qualitatively meaningful. Okay, just to close, so I showed you how to compute essentially the basic distribution in Z-contingent theory, which is the Brownian distribution and the Gluon spectrum. And then I showed that you can reformulate all of this discussion to all orders and gradients if you employ like an effective kinetic picture. So what I didn't show you today is that although we have all of these kind of theoretical tools, we don't have any meaningful observable to measure these gradients. This is difficult, first of all, because as I showed you, these effects are always suppressed by powers of energy, at least at leading order, and therefore, if you put here jet energy, this effect is really very small. And therefore, one way to try to measure them is to do more detailed calculation, which involves jet structure. And of course, the importance of this is because you are looking at the structure of the jet. Here, the denominator would be much smaller. The other nice thing is also that using this Wigner function approach, which kind of generalizes the usual approach using jet quenching, you can study more differentially the evolution of the jet, at least theoretically. So, for example, when you have zero gradients, you can also show that when you start from a non-trivial density matrix representing the quark, the evolution in the medium naturally diagonalizes the density matrix. And this is just exemplifying that even if you start with a very if you have quantum correlations inside the initial distribution for the quark, they are destroyed by the evolution in any. Finally, we also have some other progress, in particular for the evolution using massive quarks, and also including the radiative corrections to include not radiative corrections, but to resum gluon emissions to all orders in some particular kinetic machine. And yeah, that's what I wanted to say.
Okay, thank you. Let me ask any questions from the audience online?
I have a naive question. On the previous slide, maybe you said this already. I apologize if that's the case. Or maybe the previous one, I think maybe 2 slides.
This one?
Yes. So this formula that you showed, my naive question is: are you going beyond the iconal approximation? It seems like you are. Is this correct? Because of the term that is highlighted with this white dot. Is that?
So I mean, it's not true that I'm. So let me maybe explain. So let me just find the correct equation. So the point is that so when you write this term, you are taking into account some subiconal terms, not all of them, but some subiconal terms. And because, as I said, when we perform the expansion in gradients, it doesn't commute essentially with this thing. So essentially, every time you expand in gradients, it's like taking the derivative of this object. And that's why when you go to second order in gradients, it's like taking the second derivative, and you can get them which are like 1 over e squared. But of course, I mean, although you have this subiconal term, you are not doing a calculation which includes all subiconal terms. So this is so that's not kind of the goal of the calculation.
But is that sub-iconal term special in some sense that it's more important than the other ones, or is this just a mathematical effect from the non-commutation of the 2 operations? I'm trying to think of attribute a physical meaning to that term. Would it be important?
Why do we keep this term?
No, sorry. I meant the one that you show on your second to last slide, or one of the last slides. So this is a sub-iconal term, but as you said, there are other sub-iconal terms which you are not taking into account, right? And what I want to understand is is this term special in some way? Would it be enhanced for some particular observable?
No, so this term, I mean, that's what I was trying to. I mean, this term is not special, especially in the sense that it will be very suppressed because it's energy squared. What is important here is this energy independent term, because this term is leading order in the iconal expansion. That's the important term.
Okay. Thanks.
Any other question? Yeah. Let me just make a comment regarding to Farid's question. This actually is not only beyond the second term in iconal correction, because if you only consider the non-iconal correction, you can get diffusion in the transverse direction. But that you can also do that for solving the Boltzmann equation, for example, for considering even for nonlinear medium, right? So this is, but what you have considered is more than just taking count the non-iconal correction.
Okay.
It's much more than that.
Yeah, maybe.
Because just a simple non-iconal correction can give you simple diffusion equation in the transverse momentum, right? The diffusion transverse momentum is already beyond iconal.
Yes. So this term is sub-iconal, but it also is a consequence of the fact that you're considering an anisotropic.
Is non-iconal, but also not for non-uniform medium too.
Yes. So this term is special because it's an anisotropic medium. Okay.
Exactly. So I mean, if you wanted to do like a full calculation, right? What you should, and you want to go to subsubaconal accuracy, like formally, right? What you should do is first to generalize this propagator to be accurate at subsubaconal accuracy, right? Which is not the case. This is not. I mean, it will not be a path into some complicated object. But then you should redo all of this calculation using this object, which is very hard. The point is that this term that we have here is special in the sense that it's subsubaconal, but it's also coupling to the to second order gradient.
Term. Got it. And if you don't mind, I have one more question about it's going back to this interesting plot where we saw this dip in the spectrum, on the PT spectrum. So is this something, of course, as Peter said, there is, and you said there is also Sudakov effects which have to take into account, which might change this distribution. But is this something that could be potentially measurable? I know this is kind of a simple or toy model for the medium, but is this, for example, the value of CT? I don't have a good physical intuition if these values of CT are experimentally reasonable or physically reasonable in collisions that we have access to.
So I mean, that's a good question. So this CT here, I mean, the values I took here are, I mean, these values are it could be reasonable depending on who you ask, but the point here is not to do like some proper logical calculations, just to show what are the effects of having these terms. But the point here, I mean, going back to what Peter said, is that of course there is a Sudakov effect, but the point is that the Sudakov effect is not directional, so it doesn't depend on the direction you look at. Right. But this effect is directional. So what you should go is construct an observable which is not. I mean, it depends on the direction where you measure it. Then I mean, of course there are other effects which are also directions. It's not complicated, but if you were like in a medium which is like a Gaussian in 2 dimensions, right? And you construct some observable which depends on the direction where you look in the Gaussian, then you should see this effect, even if you have like Sudakov and so on top of it, because they don't depend on direction. That's the point. Of course, for QAT, which what I showed most of the time, QAT is not a good object because QAT is not direction. So what you should compute is like the tensor form of QAT, for example, which is direction.
Thanks.
Peter?
Yeah, maybe to follow up for Reid. So experimentally, it seems these kinds of measurements I talked about before, where we're looking at the angular coincidence measurement you trigger to get an axis, and you look backwards, and you look at the angular deflection azimuthally. This may be related, and just from the discussion here, and generically, it seems that the low PT jets are the effects will exhibit themselves most in low PT jets, which are the hardest to measure because of background. So I think in principle, when we may be measuring something that's related, clearly, I mean, Joao was clear, he hasn't done the actual practical calculations yet. But around hard probes, the papers, if all goes well, will come out, and maybe we discuss then how to relate these observables I shown preliminary results about previously to these kinds of deflection measurements. And of course, one has to add in the other things that are needed from field theory, in particular the Sudakov, to really make connections to experiment, but one goes one by one. So I think maybe there are some observables coming. Substructure likewise, well, that's a very hard game as you go to very low energy. The kind of inclusive and quasi-inclusive, we use experimental statistical techniques. This is not the place to describe them, to get the very low energy jets and look at what's correlated with the trigger. This may be a kind of a window into this kind of physics, but I think one has to look at the data and consider the calculations and see whether they're connected.
I see. I mean, it would be very nice to see. I mean, of course, as I mentioned in the conclusion, we are still very far away from any, what you call practical calculation. But it's the reason why we don't have a proper observable where we can kind of predict what are the effects of these gradients is that it's actually, I mean, theoretically at least, I mean, as far as I can do the calculation, it's kind of much more complicated than kind of the homogeneous case, which is what people use to compute these substructure observables. So I mean, that's why we are starting a bit, we're a bit behind in this calculation. But I mean, I think within this year we'll be able to do some calculation where we can compute at least. I mean, I hope like the effect of gradients either for jet substructure or for example, for this energy correlator that I kind of depicted here. So because this one should be sensitive to gradients, of course, to include not only gradients but also the other effects from pseudocode and so on it will be challenging. But yeah, we can discuss that probes if you are around.
Okay.
Okay, I think we will stop here and let's thank Joao again. This did not work out. Wow.
Thanks, Joao. Enjoy your time in Berkeley.
Bye-bye.
Bye-bye.
Bye-bye.